Hi, everybody. At least this is twice as many as the when you guys had your 188 midterm. So today is going to be a specialty-ish lecture. We're going to focus on core motion, iOS only. I dug and dug and dug, and you have to hack OS 10 to get the accelerometer on the MacBook Pros, and you can do it, but it's not very pretty. But on iOS, beautiful framework for handling motion sensing that works kind of hand in hand in conjunction with core location. The CM Motion Manager object is the gateway to all of the core motion functionality. So it incorporates the accelerometer data, and I'll talk about that in a second. It incorporates the rotation rate, the magnetometer data for which direction the phone is facing in absolute coordinates, and then other device motion related data like the attitude that it's, or the angle and the direction and the pitch that it's being held at. This is just kind of an overview. I'm going to talk a little bit more about these in particular in a second. You create one instance. It's a singleton. You create one instance of a CM Motion Manager one at a time. That's it. It's a common source of bugs to have multiple motion managers if you have different models within your iOS application. One instance. The CM Motion Manager receives and processes a lot of raw data. There's functionality built on top of the CM Motion Manager to help you make sense of the raw data and handle a lot of the unbelievably complicated math that goes along with motion management and motion detection. So the sensors, the Motion Manager fuses all of the raw data from the attitude, the rotation that it's moving, the magnetic field that it's in. So for the compass, it also takes into account the direction of gravity and the acceleration that it's moving. So for instance, it can tell when it's moved position, but it can also tell how fast it's moved and how fast it's accelerated on an axis. Here's what the framework looks like overall. At the very, very lowest level, you've got the raw device specific data, like the gyro data. Then above that, you've got the device motion, which starts to fuse some of the sensor data together. On top of that, you've got the accelerometer data that fuses even more of it and provides another level of abstraction. And then you have the Motion Manager on top of that. And you'll see some of these pieces. We'll peek under the hood here, and I'll show you. We'll talk about some of these pieces. We won't go completely in depth with it. This is just kind of to give you a broad overview of some of the functionality, some of the things that you can do with the Motion Manager. So, as a point of reference, you'll see a lot of the structures that are associated with this are core foundation structures, so they are actual structs, not objects. A lot of them have X, Y, and Z coordinates, as well as yaw, pitch, and roll. They've also got quaternion coordinates, so that you don't have to worry about normalization. If you don't remember what that is, Wikipedia's got some great articles on it. X in terms of relative direction. X is defined in terms of the phone moving from side to side. Y is the phone moving up and down, and Z is the phone moving in and out. This is relative to the way that I'm holding the phone now. If it's on the table, X is sliding left and right, Y is sliding forward and back, and Z is coming up off the table or down below the table. Yaw is defined as the rotation around the Z axis. Pitch is the direction around the X axis, and roll is the direction around the Y axis. This image is available in the CM Motion Manager framework reference. Also, just like all the other frameworks, very detailed, and it gives you a lot more information than I'm presenting here. This is just, like I said, a broad overview of it. So there's a couple of different ways that you can get motion data from the phone. You can specify that you want updates on a periodic rate. Say you are coordinating this with a map kit, and you're using this to sense the rate of speed that your iOS device is moving at a specific time. So you can have it interrupt you basically and tell you, it's interrupt driven, and tell you when, what the motion events are and what the current state of the motion data is. You can also sample the motion data yourself. This is most commonly used in games and other utility applications. Utility applications a lot of times will use the specified interval. Games and other entertainment that doesn't need such specific amount of data at a specific time, but needs to know the current state of the device at one time, will use a polling method where you have to manually go and ask for the current motion manager data. The polling yourself is much faster than having another thread running that's constantly interrupting you with data. So that's more utility. The interrupt is more utility and precision, whereas the polling is less precise but much faster. So with either of these approaches, you still need to call the appropriate stop methods, and we're going to talk about the accelerometer and the magnetometer in a second here. But it's really important to call these stop methods on each one of these motion manager frameworks that you use when you've finished using it. The reason why is because basically when you instantiate a motion manager object and you start asking for data, whether it's you're polling it or it's interrupt driven, it actually kicks off a couple of threads that are responsible for a lot of the really super low level hardware functionality and gathering of data, which gives some overhead, which will have some overhead for all of the iOS. So if a lot of applications have a lot of this running and they don't stop the data collection, your app and other apps are going to be sluggish unless your app is killed off or put to sleep. If it's put to sleep, it'll stop collecting data, but as soon as it comes back awake again, it'll start collecting data whether you're polling or being interrupted with it or not. So it's really important to call these stop update methods when you're done with your data. So here's what getting updates at specified intervals. Here's what the interrupt sequence looks like. For the accelerometer, you call the set the update interval property gives you the currently set, and you can set the interval, the time interval that you want to be interrupted with motion manager data. In this case, accelerometer data. You call start accelerometer updates to queue with handler. You have to provide a queue. You have to provide the higher level data structure that's going to hold the information as it comes in from the lower level. You supply a block. We're going to talk more about that in a second. For the handler, and your block will be called with the accelerometer data at your specified time intervals. The data is actually passed in as accelerometer data objects. These and actually I'll show you what the data types actually look like in a couple of slides. The gyroscope has a gyroscope update interval. Same deal. Start the gyro updates, giving it a queue and giving it the handler, the block handler. Rotation data comes in from the gyro handler, and that's passed into your block in gyro data objects. The magnetometer follows the exact same pattern. Update interval, updates, you pass it with the queue, and the handler, the block handler, you get magnetometer data objects into your handler block. So Device motion is kind of a layer on top of all of these different frameworks. It fuses a lot of this stuff together. The device motion update interval is a property that you can specify where you want to be interrupted with the device motion, the all-encompassing kind of device motion data. What's different about the device motion is that in iOS 5 you can actually pass a reference frame so that you can get relative data out of the device motion from the device motion framework. Otherwise, what you're getting back, the relative information or the absolute information that you're getting back, Apple provides you with a lot of constants that you can use to calculate like exactly where your device is in space and where and exactly what angle it's tilted or yawed or rolled at, and it's the direction that it's facing with the compass. What's really nice about in iOS 5 is that they allow you to pass a reference frame in so that you get all the data that you get back is relative to the current position. So if you have say a game that like a flying game, and the user is holding your device at a specific angle, and you're just using absolute data to control the way that the plane is flying, the pitch and the yaw and the roll of the plane. If you're not using a reference frame, then depending on where the game is starting or where you start the game, you may the object that you're using to control the plane will immediately start to react to the yaw and the pitch and the roll that the user starts the application at. If you specify the current orientation of the device as the reference frame, then you'll just get relative coordinates or relative data from that point on. Does that make sense? So you'll get, if they're holding it at an angle, you can still let them do nose down and nose up, say, which is pretty common for flying games, that's relative to the current position that they're holding at. So if they're looking down at the top of it, it'll act just the same 15 degrees forward and 15 degrees back as it will if they're holding it up straight up and down and going 15 degrees forward or 15 degrees back with it. So if you want to do your own sampling of the data as opposed to being interrupt driven, with the accelerometer, you just say start accelerometer updates, and it will start in the background collecting the data. You can access the CM accelerometer data object by reading this property. Accelerometer data is a property that's exposed from the CM, let's see, the CM Motion Manager exposes this property that you can use, and you can query this at any time that you want. And as long as you've called the start updates and you haven't stopped the updates, it'll keep updating this property with the current motion values that the sensors are picking up. Same thing with the gyroscope, follows the same pattern. Start the updates. You'll access the gyro data property and get CM gyro data objects back. I'm going to show you what these look like in a second. The magnetometer, exactly the same thing. Start the updates. It'll start collecting information. You can get the CM magnetometer data objects out of the magnetometer data property. So, device motion, same thing. This is the same device motion objects that I was just speaking about in terms of the reference frame. This is how you would use it in a polling situation as opposed to an interrupt situation. It kind of fuses those two, kind of fuses the same idea as start getting the updates and querying a property for the actual data, except in this case, and with the device motion, you can actually pass in a reference frame to get relative data back out of the sensors. So, how do you detect whether the hardware is available or not on the iOS devices? If it's not available, It's not going to crash. It's just not going to give you back any data. But your application isn't gonna crash or start throwing exceptions. It just won't do anything. To find out if the feature's available, you use the properties of the CM Motion Manager, like gyro available, gyro is active. You can use it to check for the accelerometer and for the magnetometer as well. These are all outlined in the documentation. So here's what the motion event blocks look like. Kevin talked about blocks earlier, so I'm not going to recover them. There is a reference URL at the end of these slides if you need an update on the syntax of these blocks. But this is what the blocks look like, and they all follow the same pattern. They don't return anything, but they do take the specific type of core motion data objects in as a parameter, and you also will get passed in a pointer to an error as well. I'll show you what this error object looks like in just a second. So here's what the accelerometer data looks like. It is 3 double precision values, X and Y and Z. It's all measured in terms of the gravitational force in 9.81 meters per second squared. That's later. There's also a constant that for the accelerometer data for gravity, so that you can subtract that out away off of your acceleration data to get relative acceleration. CM attitude is an object that is the device's attitude, the direction that it's tilting, yawing, rolling, or pitch. At any specific point in time. It's relative to the frame of reference that I talked about earlier. There's 3 different representations for a device's attitude. There's the rotation that it's currently in, and that's defined in terms of a matrix. If you're familiar with like 3-dimensional graphics and you're familiar with rotation matrices and translation matrices, you can get this data as a rotation matrix. You can also get a quaternion so that you don't have to try and figure out the normalization, the direction of the rotation vector, or you can get just raw Euler angles, the yaw and the pitch and the roll, the roll, pitch, and yaw values. So quaternion, the CM quaternion is a type in CM attitude that represents it's a measure of the attitude X, Y, and Z, and then a W. It's the rotation of W around the point X, Y, and Z. Like I said earlier, you can look Wikipedia's got a good article on quaternions if you can't remember them from, is that trig? The CM reference frame, which I spoke about before, that you can pass into the device motion calls when you start your updates to get relative updates. They have constants that have been declared and defined. You can say that you can pass in a reference frame where the X is arbitrary. Remember, that's side to side, and the Z is the vertical. You also have a reference frame that you can correct for. That you can correct the reference frame using the magnetometer, and if it's been calibrated correctly, it can give you super accurate attitude results using the magnetometer as a point of reference, as opposed to just what the other sensors are telling the low level functionality, where what the device's current state is in. You can also, if the magnetometer exists, you can also use magnetic north as a reference frame, and then you can also use true north, which is calibrated. If you want to learn more about this, especially in terms of using it with core location, there's a bunch of documentation on it. I just want to let you know that Apple has got defined a whole bunch of reference frames already that you can use, and it can utilize some of the other sensors that are available on the iOS devices. So the gyro data represents just a single measurement in the rotation rate It looks like this. It's an X and a Y and a Z. It follows the right-hand rule, if you remember that from physics and from trig, I believe. If the right hand is wrapped around the axis, like the x-axis, then the positive is towards where your fingertips are pointing, and negative is pointing the other direction. So if the x-axis, which is side to side, is our reference angle, then positive or rolling forward will be the direction that our right hand's fingers are pointing. There's also really good pictures on Wikipedia if you want to see some more about, and you need to understand how the relative directions that come in, the relative data that comes in on with these vectors, how they relate to each other in terms of positive, like a positive motion versus negative motion or negative rotation rates. So the magnetometer data it's all of the measurements that are recorded by the magnetometer. It's different than what core location uses. Core location uses the magnetometer in terms of using the compass and which direction you're pointing and which direction you're moving. This just represents the raw underlying data. So it's the magnetic field in X, Y, and Z in microteslas. It's actually pretty cool to take a look at these and print them out, the values out as you move the device around and watch how quickly this responds to and how well what precision this is recorded at. To look at the difference between polling and getting updates at a specific interval. So device motion, like I said earlier, kind of encapsulates everything, kind of puts it all together in a neat package for you. It can take into account the direction that the device is moving relative to the Earth, and can take into account gravity as well. It has two different motion vectors in terms of acceleration. It has user acceleration that strips out the gravity component, and then it's got an absolute acceleration that will include the gravity component. Since it can track the device with both the gyroscope as well as the accelerometer, core device will fuse the data together, but you need to differentiate between gravity acceleration and user acceleration if you're using the accelerometer in relation to the gyroscope. The device motion object, it's really nice. It has both measurements in gravity and the user acceleration properties. It can split those up independently for you, so you don't have to do all the math. The device motion is also there's also the calibrated magnetic field. If you've used the compass on the iPhone 4s, was it iOS 4 or only iPhone 4s? iPhone 4s on up. You can see that you'll see certain times where it needs to be recalibrated, where you have to move it in the figure 8. This actually these are the fields that actually can tell tell the operating system, or that can tell the compass when it needs to be calibrated. You can find out what the current magnetic field is, and you can also find out the accuracy as well. The accuracy field comes out with one of these constants if it hasn't been calibrated yet, if it's low, medium, or high. Every single one of the motion devices subclasses off of what's called a log item. Since it's the base class, every one of the core motion the core motion frameworks have this functionality built into it. What's really cool is that it will time tag the data so that you can go back through and reconstruct, say, how far a device has moved over a specific period of time, or how far a device has accelerated along a certain axis over a certain period of time. It has a time. It's a timestamp property that's part of the log item. This is the base class is available in every one of the motion, the core motion frameworks. So you can read this timestamp property. A lot of times people will log all this data to a file so that they can replay it back later. It records every time a measurement was taken, and the time that it reports back is the number of seconds since the phone was rebooted. The CM error, like I'd shown you previously in the blocks and your handlers, the error null is when there's been no error, and these are all enumerated constants. There's also a require movement. If you ask for what the acceleration is of the device at the current time and the device hasn't moved, then your handler will get this error. Every time it's called, it will say that the device actually has to move before it can start calculating acceleration along a certain vector. And then if you're using the true north reference frame and it can't find the device's location yet to compare it to the magnetic north, then you'll get this error here, the true north not available yet. So today's lab that will be up in a moment is the accelerometer graph project. It looks. I'm only going to show you demo this in little tiny screen so that you can't see it, so that you actually have to do it yourself. But it's really super cool. As you start to move the device, you can see the acceleration along all of the different axes in real time. And it also has a high pass and low pass filter, as well as having an adaptive filter, so that you can see that bumps and jars. Like, say, if somebody was riding in a car and you have there's bumping and jarring going on, you may want to filter that data out. For your, say, if you've got a game that relies on user movement, you may want to desensitize those bumps and jars. And this project, the sample code, actually has all of the code to do that, it's actually pretty cool. So it's optional. I highly recommend that you try it, because to actually get data out, it has to be running on your device. Simulator won't show you anything. Even if you do the shake in the simulator, which kind of surprised me, it still won't show that they don't have like hardware thunks in the simulator, apparently, to simulate the motion, the device motion, at least from what this app is using. So you have to get it running on your phone, or your iOS device. It also works on the iPod as well. So to get it working, you have to code sign your app. If you haven't done that yet, now is an excellent time to get that to work. Since Kevin and I are here, especially Kevin, since Kevin is responsible for the provisioning of devices and making sure that they're code signed correctly, this is a really good opportunity to practice and make sure that you understand the whole process of provisioning and code signing and getting your applications running on your device. If you don't have the identity yet, if you haven't sent your iOS devices UUID to Kevin to set you up with a profile, talk with him about that. But under the build settings in the project, if you try and build it, run it as it stands, it won't build. It won't build to the device. You have to code sign it. It's under the build settings under code signing. You'll see where you can do that. Read up on the documentation if you haven't done it yet, and send your UUID to Kevin if you need a profile. And I believe, yes, so a couple of references. So here's the Core Motion, Apple's Core Motion reference. Here are the motion events, event handling that can occur. You can set up event handling that occurs when motion events happen. So you can be motion event driven. That's usually a lot more useful for utilities. There's also the Motion Manager class reference and all the fields in that. And then here's a refresher on block programming if you forget the syntax for block programming in Objective-C. And that's it. Questions? I know, that was quick overview. If I pretty much intended that if this kind of gives you just a flavor of what's available and the data that's available. But if you want to, if your project or any of your future applications, you want to use motion or you want to use the acceleration or the magnetometer, or the gyroscope, these are the places where you start diving into the documentation to learn more about how to use them. Cool. That's it.